perfect geometric shape is locked around Saturn's North Pole. 6 sides, 6 corners, nearly 4 Earths wide, and despite decades of observation, no one can fully explain why it exists. Inside that hexagon, winds race at hundreds of miles per hour. Storms churn through the atmosphere of a planet almost 1 billion miles from the Sun. Yet the shape itself remains astonishingly stable, as though someone had drawn it with a ruler across the clouds. Nothing like it has ever been found anywhere else in the solar system. But the hexagon is only the beginning. Saturn is surrounded by 146 known moons. One of them is ejecting enormous plumes of water into space right now. Hidden within that water are chemical ingredients associated with life, released from an ocean buried beneath a shell of ice. The eruption has likely been happening for longer than human civilization has existed. Then there are the rings. For centuries, they have been the defining symbol of Saturn, yet scientists now know they are surprisingly young and they are disappearing. Every year, material from the rings rains down into the planet below. In 2025, they even seem to vanish from Earth's perspective altogether. And when NASA's Cassini spacecraft finally reached the end of its mission after 13 years exploring the Saturn system, the agency made a remarkable decision. They destroyed it. Not because the spacecraft had failed, because some of the worlds it had discovered appeared too important to risk contaminating. What unsettled scientists most was that many of Saturn's biggest mysteries emerged only after years of studying the data Cassini left behind. Some of the strangest discoveries arrived after the spacecraft itself was already gone. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. Now, let's begin. Long before spacecraft crossed the darkness between worlds, Saturn belonged entirely to the eye. Across deserts, river valleys, and ancient cities, people watched a pale wandering light move among the stars. The ancient Babylonians recorded its motion as early as 700 years before the Common Era, tracking its slow journey with remarkable care. They knew nothing of rings or moons, yet they understood that this object behaved differently from the fixed stars above them. Centuries passed. New tools arrived. In 1610, Galileo Galilei turned one of the earliest telescopes towards Saturn and saw something baffling. On either side of the planet appeared two rounded protrusions. He described them as ears. The instrument available to him lacked the resolving power needed to separate Saturn from the structure surrounding it. To Galileo, the planet seemed misshapen, almost unfinished. The mystery lingered for decades. Then, in 1655, the Dutch astronomer Christian Huygens observed Saturn through a more capable telescope. What had appeared as ears finally resolved into a ring. A single insight transformed generations of confusion. Suddenly, Saturn became something entirely different, a world unlike any other known planet. Yet even after that breakthrough, distance remained a barrier. For roughly 300 years, everything we learned about Saturn came through reflected sunlight. We studied changes in brightness. We mapped the rings. We discovered moons. But all knowledge arrived from far away, filtered through vast stretches of space and the limitations of telescopes on Earth. Then humanity began to travel outward. In 1979, Pioneer 11 became the first spacecraft to visit Saturn. It swept past the planet and returned extraordinary images. A year later came Voyager 1. Another year passed, and Voyager 2 followed. Each encounter lasted only days, brief glimpses during much longer journeys. Data poured back to Earth. New moons appeared, Ring structures emerged in surprising detail, and something else surfaced. Near Saturn's North Pole, Voyager images revealed an unusual shape. A six-sided pattern seemed embedded within the atmosphere. Scientists noticed it, documented it, and moved on. The observations were too brief to fully investigate. There were simply too many discoveries competing for attention. But Saturn was waiting. In October of 1997, the Cassini-Huygens mission launched toward the outer solar system. It was a partnership between the National Aeronautics and Space Administration, the European Space Agency, and the Italian Space Agency. Over 7 years, the spacecraft traveled 3.5 billion kilometers, which is about 2.2 billion miles, before reaching Saturn in 2004. What followed changed everything. Cassini completed 294 orbits over 13 years, studying Saturn with a persistence no previous mission could match. For the first time, we were not passing by, we were staying. And even now, years after the spacecraft itself became part of Saturn's atmosphere, scientists continue uncovering discoveries hidden within the immense archive it left behind. Among the countless images returned by Cassini, one stood apart almost immediately. It was not a moon, a ring, or an unexpected object drifting through space. It was a shape so familiar that your mind recognizes it before your scientific instincts accept it. Six sides. When Cassini reached Saturn's north polar region in 2006, the spacecraft confirmed that the strange feature glimpsed decades earlier was real. Planetary scientists reacted with genuine shock. They were looking at a hexagon carved into the atmosphere of a gas giant, a geometric pattern spanning roughly 32,000 kilometers, which is about 19,884 miles. Nearly four Earths could fit side by side within its boundaries, and it was holding together. The atmosphere of Saturn is a place of motion. Gases rise and fall, winds accelerate, storm systems merge, stretch, and dissipate. Yet the hexagon remains sharply defined. Along its edges, a powerful jet stream raced at speeds approaching 500 kilometers per hour, which is about 311 miles per hour. Those winds traced the six-sided boundary with remarkable precision. The deeper scientists looked, the stranger it became. Measurements suggested the walls of the hexagon descended at least 100 kilometers, which is about 62 miles, into the atmosphere below the cloud tops. Some models hinted at far greater depths. The true extent remains uncertain. Even today, researchers continue debating how far the structure penetrates into Saturn's interior layers. Its motion offered another surprise. The six corners circle the center at nearly the same rate as Saturn's deeper interior. Because of that consistency, scientists use the hexagon as a kind of natural clock, helping estimate the planet's rotation. Few atmospheric features remain stable enough for such a role. This one has done so for decades. On Earth, storms rarely behave this way. Rotating systems naturally curve into circles and spirals under the influence of fluid motion and planetary rotation. Geometric boundaries are not expected outcomes. A long-lived hexagon seems to push against the instincts developed from studying atmospheres across our own world. Researchers searched for answers wherever they could. In 2010, experiments at the University of Oxford created hexagonal patterns within rotating tanks of fluid. The results demonstrated that such shapes were physically possible under carefully tuned conditions. But those laboratory setups depended on precise balances of speed and fluid behavior that proved difficult to maintain naturally. Meanwhile, other planets offered little guidance. Jupiter hosts storms of astonishing scale, including the Great Red Spot, a vortex larger than Earth itself. Yet Jupiter's storms remain rounded and irregular. None settle into stable geometry. None draw straight edges across a planetary atmosphere. Year after year, the hexagon endured. Voyager observed it. Cassini confirmed it. The Hubble Space Telescope continued tracking it afterward. Across more than 4 decades of observation, its shape persisted. Nothing else in the solar system has matched it, and Saturn offered no explanation. A year after Cassini disappeared into Saturn's atmosphere, its work continued from computer screens and archived measurements. Researchers were still sorting through observations gathered during the spacecraft's final years. Hidden within that enormous collection of data, an unexpected pattern emerged. The shape looked familiar. High above the cloud tops, in a region known as the stratosphere, scientists found another hexagon. The stratosphere is an upper atmospheric layer where temperatures and winds behave differently from those below. Yet there it was, suspended far above the famous polar feature already known to science. The resemblance was remarkable. This upper hexagon matched the lower one almost perfectly, each side aligned with its counterpart, each corner pointed in the same direction. Viewed together, the two structures appeared stacked one above the other, separated by vast layers of atmosphere. At first glance, that might seem merely unusual, but atmospheric scientists immediately recognized a deeper problem. Between the lower hexagon and the upper one lie regions where wind directions reverse completely. Air currents that move one way below begin moving another way above. Those transitions create barriers that typically disrupt large wave patterns traveling through an atmosphere. Physics predicts interference. A concept known as evanescence describes what happens when a wave enters a region where it can no longer continue propagating. In plain terms, the wave gradually fades away. Its energy is absorbed or scattered before it can pass through. Under those conditions, a structure linked to the lower atmosphere should lose coherence long before reaching higher layers. Yet the second hexagon remained. The discovery drew particular attention from Dr. Lee Fletcher of the University of Leicester, who led the investigation. As researchers examined the measurements, they found themselves confronting a phenomenon that existing atmospheric models struggled to accommodate. The geometry appeared where theory suggested it should not survive. But observations left little room for doubt. One possibility proposes that the two hexagons are connected through an unknown coupling process. Coupling, in atmospheric science, refers to different layers influencing one another despite being physically separated. Some mechanism could be transmitting information between the regions, preserving the shared shape even across disruptive wind boundaries. Another idea reaches much deeper. Far below the visible atmosphere lies Saturn's vast interior, dominated by compressed hydrogen under extraordinary pressure. Some researchers have wondered whether processes originating far beneath the clouds could impose large-scale patterns upward through the planet. In that scenario, the hexagons would be surface expressions of something rooted much farther down. Neither explanation has gained confirmation. As studies continued through 2026, the upper hexagon remained resistant to clear interpretation. The observations are real. The alignment is real. The atmospheric barrier between them is real as well. For you and me, that combination is what makes the discovery so compelling. Saturn had already presented a geometric storm unlike anything known elsewhere. Then the planet revealed a second copy, placed above the first in a location where current understanding says it should not be. The shape persisted. The explanation did not. Stand at the center of the puzzle, and the geometry begins to fade. Beneath the six-sided boundary lies something far more familiar, at least at first glance. Nestled within the heart of Saturn's northern polar region is a hurricane, a real one. When Cassini peered into the center of the vast atmospheric structure, it found a clearly defined eye surrounded by towering clouds. Anyone familiar with satellite images of terrestrial hurricanes would recognize the pattern immediately. The resemblance was striking. Scale changed everything. The eye alone measures roughly 2,000 kilometers across, which is about 1,243 miles. That is comparable to the distance between New York and Denver. What appears as a small feature inside the larger structure is itself immense by planetary standards. Around that eye, winds accelerate dramatically. Measurements showed speeds reaching approximately 530 kilometers per hour, which is about 329 miles per hour. Those velocities exceed the strongest hurricanes ever recorded on Earth by more than a factor of two. Clouds circle the center in a vast atmospheric whirl, maintaining an organization that persisted throughout years of observation. But familiar shapes can hide unfamiliar causes. On Earth, hurricanes draw energy from warm ocean water. Heat and moisture rise from the sea surface, feeding powerful, rotating storms. Remove the ocean, and the storm weakens. The connection is direct and well understood. Saturn offers no such source. There is no solid ground beneath the clouds, no tropical sea, no liquid water reservoir waiting below the atmosphere. As we follow the storm downward, the environment becomes increasingly alien. Layers of hydrogen and helium stretch deeper and deeper into the planet, transitioning gradually into regions of immense pressure. Yet the hurricane remains active. Researchers believe the driving force may come from deep thermal convection. Thermal convection is the movement of material caused by heat differences. Warm material rises while cooler material sinks. Inside Saturn, heat left over from the planet's formation, along with energy released through ongoing internal processes, continues moving outward through the atmosphere. That rising energy may sustain the storm. Cassini revealed another surprise while examining its structure. Early estimates suggested the hurricane extended about 100 kilometers below the cloud tops, which is about 62 miles. Later modeling efforts pointed toward a much greater depth. Some analyses indicated that the circulation could penetrate thousands of kilometers into Saturn's atmosphere, which is about hundreds to thousands of miles depending on the depth considered. The deeper scientists looked, the harder the storm became to define. But the northern pole was not alone in hosting a hurricane. Saturn's southern pole also contains a massive cyclonic system. It possesses an eye. It possesses strong winds. It displays many characteristics expected from a giant planetary hurricane. One feature is missing. There is no hexagon surrounding it. The southern storm appears broadly circular, behaving much closer to expectations. The northern storm exists inside a geometric framework, unlike anything known elsewhere. Two poles occupy the same planet. Both receive energy from the same world. Both rotate beneath the same sky. Yet they seem governed by different rules. From hundreds of millions of kilometers away, Saturn appears almost impossibly simple. A golden sphere sits at the center, surrounded by broad, luminous bands that seem smooth and continuous. Through small telescopes and even larger observatories, the rings can look like solid structures carefully placed around the planet. The reality is far stranger. Those bright bands are not surfaces, they are swarms. Countless individual fragments orbit Saturn together, each following its own path through space. Some particles are no larger than grains of sand. Others rival houses in size. Most consist largely of water ice mixed with rocky material, reflecting sunlight with remarkable efficiency. What appears unified is actually fragmented. The ring system stretches across approximately 282,000 kilometers, which is about 175,227 miles. That distance exceeds the span between Earth and the Moon and then continues farther still. Yet, for all that width, the average thickness of the main rings is only about 10 meters. The proportions feel almost impossible. If you could somehow shrink the rings to the size of a sheet spread across a room, their thickness would become almost unimaginably slight. Relative to their width, they are thinner than a sheet of paper. Saturn's most iconic feature resembles a solid disk only because distance hides its delicate structure. But the rings are not a single entity. Astronomers divide them into separate regions known as the D ring, C ring, B ring, A ring, F ring, G ring, and E ring. Each region possesses its own density, particle population, and behavior. Some are bright and crowded, others are diffuse and difficult to see. Together, they form a system far more intricate than early observers ever imagined. As Cassini moved among them, details emerged that challenged expectations. Researchers found razor sharp boundaries where particles seemed confined with surprising precision. Waves rippled through the rings, like patterns spreading across water. Small embedded objects, carved propeller, shaped disturbances into the surrounding material. These hidden moonlets, tiny natural satellites too small to dominate their surroundings, revealed themselves through the marks they left behind. One structure proved especially remarkable. A vast spiral corrugation extends approximately 19,000 kilometers, which is about 11,807 miles, across part of the ring system. Scientists traced its origin to a comet impact in 1983. That collision nudged ring particles into slightly tilted paths. Decades later, those altered orbits continue winding together, preserving evidence of an event long past. Nothing here stands still. Gravity from Saturn's many moons constantly reshapes the rings. Every orbit introduces subtle changes. Every close passage leaves traces. The system behaves less like a static object and more like an evolving environment where countless interactions unfold simultaneously. New moons emerged from this process of observation as well. Several satellites entered astronomical catalogs only after Cassini arrived. Before the mission, nobody knew they were there. Saturn's rings had concealed them within a landscape already rich with motion, structure, and complexity beyond anything visible from afar. Imagine watching a coastline erode grain by grain. No single moment reveals the change. Yet over time, the landscape becomes something different. Saturn's rings are undergoing a similar transformation, except the process unfolds across a planetary scale. Material is leaving constantly. During its years among the rings, Cassini discovered that tiny, charged particles of water ice do not always remain in orbit. Saturn's magnetic field reaches outward and interacts with those particles, gradually pulling some of them toward the planet. Scientists call this process ring rain. The name sounds gentle. The reality is immense. Measurements indicated that between roughly 432 and 2,870 kilograms of material may fall from the rings every second. Converted across an entire day, the upper estimate approaches 10,000 tons. Saturn is steadily absorbing pieces of the structure that made it famous. But this is not a distant theoretical calculation. Researchers detected the process directly through changes occurring in Saturn's upper atmosphere. Ring material enters the atmosphere and alters its chemistry, providing measurable evidence that the transfer is happening right now. The rings are losing mass in the present, not in some unimaginably remote future. How long can that continue? At the lower end of the estimated loss rate, the rings could survive for around 300 million years. At the higher end, their lifespan becomes substantially shorter. 300 million years sounds vast when measured against a human life, yet planetary history operates on a different scale. Earth itself formed approximately 4.5 billion years ago. Complex multicellular life has existed for roughly 500 million years. Against those timescales, a remaining lifespan of a few hundred million years begins to feel surprisingly brief. The rings are enduring, yet they are not permanent. Observatories continue tracking the process. The James Webb Space Telescope studies how seasonal changes influence the rate of ring rain. As Saturn travels around the Sun, the angle of the rings shifts relative to incoming sunlight. Those changing conditions affect how particles become electrically charged and how efficiently material migrates toward the atmosphere. The story becomes even more intriguing when scientists consider the rings' age. Current models suggest they formed somewhere between 10 million and 100 million years ago. If those estimates are correct, the rings are newcomers. Dinosaurs dominated Earth long before the younger age estimates placed the rings into existence. For most of Saturn's history, the planet may have looked dramatically different. A ringless Saturn is entirely possible. And one day, that appearance may return. The planet likely spent billions of years without the brilliant structure we associate with it today. Future ages may see the same outcome again as ring rain gradually dismantles the system, particle by particle. That realization changes how we view the sky. You and I exist during a remarkably narrow interval, a period when Saturn possesses rings large enough to transform its appearance and bright enough to be seen from across the solar system. The view feels timeless. The measurements tell another story. There are moments in astronomy when nothing physical changes, yet everything appears different. The spring of 2025 brought one of those moments. Across telescopes around the world, Saturn seemed to lose the feature that made it instantly recognizable. The rings faded from view. They had not vanished in any physical sense. Their particles continued orbiting exactly as before. The immense structure remained intact, but from Earth's perspective, geometry briefly rewrote the scene. Our viewing angle shifted. Every 13 to 15 years, Earth passes through Saturn's ring plane, the flat orbital layer occupied by the ring particles. During this alignment, the rings turn edge-on to observers on Earth. Instead of presenting their broad surfaces, they reveal only their incredibly narrow thickness. That thickness is astonishingly small. The rings span approximately 282,000 kilometers, which is about 175,227 miles across their width, yet their average thickness remains close to 10 meters. Viewed edge-on from hundreds of millions of kilometers away, such a structure becomes extraordinarily difficult to detect. The effect is almost deceptive. Imagine trying to spot the edge of a sheet of paper from across a large room. The object still exists. Light simply has very little surface to reflect toward you. Saturn's rings entered a similar state, becoming so thin from our perspective that the planet appeared stripped of its most famous characteristic. Astronomers call this alignment a Saturnian equinox. The previous event occurred in September of 2009. Another arrived during 2025 as the changing positions of Earth and Saturn recreated the necessary geometry. For a brief period, amateur observers and professional researchers witnessed an unusual sight. Saturn resembled a smooth golden sphere suspended against the darkness. A familiar symbol disappeared, but scientific opportunities emerged immediately. The Hubble Space Telescope used the alignment to investigate vertical structures within the rings. Features normally hidden by reflected light became easier to isolate. Wave patterns stood out more clearly. Small, embedded moonlets left traces that were easier to identify under these conditions. Other observatories benefited as well. The National Aeronautics and Space Administration and the James Webb Space Telescope took advantage of the reduced glare. With less reflected light interfering, researchers obtained cleaner measurements of material entering Saturn's atmosphere. Those observations improved studies of ring rain and helped refine estimates of how rapidly the rings continue losing mass. The rings gradually returned as Saturn's orientation changed. Yet the event carried a deeper implication. For centuries, every culture that observed Saturn saw a ringed world. The image became inseparable from the planet itself. We often treat that appearance as permanent, almost timeless. The evidence suggests otherwise. Current estimates indicate the rings may survive only a fraction of Saturn's total lifespan. Hundreds of millions of years from now, future observers could look toward the same region of space and find a giant planet without the luminous bands that define it today. For a few weeks, in 2025, geometry offered a preview of that distant future. If you looked down upon Saturn's brightest ring at the right moment, you might notice dark streaks stretching across its surface. They appear suddenly, they linger briefly, then they fade away again. For decades, these markings have challenged attempts to explain how the ring system truly behaves. Scientists call them spokes. The name comes from their appearance. Each feature extends outward across the ring in a radial pattern resembling the spokes of a wheel. They cut across the surrounding material rather than following the curved paths we expect from orbiting particles. Against the bright background of the B ring, they often appear as dark shadows painted across the ice. Their history is unusual. The first observations came from the Voyager spacecraft during the 1980s. Researchers were intrigued, but uncertainty remained. After the initial detections, the spokes seemed to vanish. Some scientists began wondering whether they had been artifacts, false patterns introduced by imaging systems rather than genuine structures within the rings. Then they returned. The Hubble Space Telescope confirmed their presence again in 2005. Cassini later observed them repeatedly throughout its 13 years around Saturn. The phenomenon was undeniably real, yet understanding it proved far more difficult. The problem begins with orbital motion. According to classical orbital mechanics, particles closer to Saturn travel around the planet more quickly than particles farther away. This difference in speed should rapidly distort any straight structure extending across multiple orbital distances. A radial feature ought to stretch and twist into a spiral almost immediately. But the spokes resist that fate. For a period of time, they maintain their shape. They move with the surrounding ring material, then gradually drift. Eventually, they begin traveling at a different rate than the particles below them before dissolving back into the background. Their behavior suggests that something is temporarily freeing them from the ordinary rules governing the ring's surface. One leading explanation involves electrostatic levitation. Electrostatic levitation occurs when electrically charged particles are lifted by electromagnetic forces. In Saturn's rings, tiny grains of dust may acquire electrical charges and rise above the surrounding material. Once elevated, they become more strongly influenced by Saturn's magnetic field than by the local orbital motion of the ring particles beneath them. That possibility helps explain their movement. It does not explain their birth. Researchers still do not know what triggers the charging process across such large areas at nearly the same time. Some spokes extend across hundreds of kilometers, which is about 62 to several hundred miles, depending on their size. Something must initiate those changes with remarkable coordination. Observations after Cassini added another layer to the mystery. The Hubble Space Telescope continued monitoring Saturn and discovered that spokes appear more frequently around Saturnian equinoxes. Those are periods when sunlight strikes the rings from a changing angle. The pattern hints at a connection between illumination and electrical charging, but hints are not answers. The relationship remains incomplete. Models reproduce portions of the phenomenon, yet none fully capture the timing, structure, and evolution of the spokes. Across one of the most studied planetary ring systems ever observed, dark lines still emerge without warning and disappear before science can fully account for them. Count them one by one, and Saturn's family becomes astonishingly large. The planet currently possesses 146 confirmed moons, more than any other planet in the solar system. Most are small, some are irregular, a few are genuinely remarkable, yet one of them seems determined to blur the boundary between moon and planet. That world is Titan. Its diameter measures approximately 5,150 kilometers, which is about 3,200 miles. Titan is larger than Mercury and ranks as the second largest moon in the solar system, surpassed only by Ganymede, a moon orbiting Jupiter. Size alone makes Titan noteworthy. But size is only the beginning. The atmosphere changes everything. Titan remains the only moon known to possess a dense atmosphere. A thick orange haze wraps around the entire world, concealing the surface beneath layers rich in nitrogen. Atmospheric pressure at the surface exceeds Earth's sea level pressure by roughly half again as much, creating an environment unlike any other moon we have explored. Reaching the ground took time. In January of 2005, the Huygens lander separated from the Cassini spacecraft and began its descent. The atmosphere was so substantial that the journey lasted approximately 2 hours and 27 minutes. Parachutes slowed the probe steadily as it drifted through layers of haze toward a landscape no human instrument had ever touched. Eventually, it arrived. For 72 minutes after landing, Huygens transmitted data back through Cassini. The images revealed rounded pebbles scattered across the terrain, channels and drainage features cut through the surface. Everything suggested the action of flowing liquid. But the liquid was not water. Surface temperatures average around negative 179 degrees Celsius or negative 290 degrees Fahrenheit. Under those conditions, water becomes as hard as rock. Rivers of liquid water cannot exist there. Instead, another substance takes over the role water plays on Earth: methane. Titan possesses a complete methane cycle. Methane evaporates from lakes and seas. It rises into the atmosphere and forms clouds. Those clouds produce methane rain. Rain feeds rivers. Rivers carry material across the landscape and eventually return it to larger bodies of liquid. The resemblance to Earth is extraordinary. Entire coastlines have formed around methane seas. The largest, known as Krakenmeer, rivals some of the greatest inland seas on our own planet. Standing on Titan, you would recognize many familiar geological patterns, even though the chemistry behind them is fundamentally different. That combination fascinates planetary scientists. Here is a world with weather, seasons, rainfall, rivers, shorelines, and atmospheric circulation operating under conditions that would be lethal to life on Earth. Yet the processes themselves feel strangely familiar, as though nature has rewritten a known story using entirely different ingredients. Because of that, Titan remains a priority destination. The Dragonfly mission is currently scheduled to launch in 2028 and arrive in 2034. This nuclear powered rotorcraft will fly from location to location across Titan's surface, examining organic chemistry and searching for clues about the chemical pathways that may precede life itself. Beneath Titan's familiar surface features, hidden far below the methane seas and drifting orange haze, another world seems to exist. We cannot see it directly. No spacecraft has drilled down to it. Yet its presence reveals itself through motion. As Titan circles Saturn, the giant planet's gravity gently pulls and releases the moon. The process creates tidal deformation, a slow flexing of the entire body caused by changing gravitational forces. When scientists examined measurements collected during repeated Cassini flybys, they found Titan was bending more than a completely frozen world should. The amount of flexing pointed toward something unexpected. Somewhere below the crust, a liquid layer appeared to be absorbing and redistributing that energy. An ocean. Current estimates place this buried ocean roughly 100 to 200 kilometers beneath the surface, which is about 62 to 124 miles below the ice. That depth makes it far more difficult to reach than the hidden ocean inside Enceladus. Between us and the water lies an immense shell of frozen material. Even so, the evidence has grown steadily stronger. But the ocean is only part of the story. Titan's atmosphere contains an astonishing variety of organic compounds. Organic molecules are carbon-based chemicals that form the building blocks of life as we know it. Cassini identified hundreds of these compounds, creating a picture of chemical complexity unmatched anywhere else beyond Earth. Many of the same molecules also appear in meteorites and in the vast clouds between stars where planetary systems are born. Among those discoveries was a compound called acrylonitrile. Computer simulations later suggested that, under Titan's exotic conditions, acrylonitrile might assemble into structures resembling biological membranes. On Earth, membranes formed from phospholipids create boundaries around living cells. Those boundaries help separate life from its surroundings. Theoretical studies proposed that a similar role could be played by entirely different molecules within liquid methane. The implication was startling. Could life function without liquid water? Could biological chemistry operate inside methane instead, using a completely different solvent? For generations, such questions belonged largely to speculation. Titan helped move them into serious scientific discussion. Debate continues. No evidence for methane-based life has been found, yet the possibility is now examined through research papers rather than pure imagination. Meanwhile, material from the atmosphere continually settles onto the landscape below. Fine hydrocarbon particles drift downward and accumulate across vast regions. Over immense spans of time, winds shape these deposits into towering dune fields. Cassini measurements revealed dunes reaching approximately 100 meters in height and stretching for hundreds of kilometers, which is about 62 miles or more across the surface. But one location draws particular attention. Dragonfly is expected to explore the region surrounding Selk Crater, an ancient impact scar where a violent collision may once have melted surface ice. For a limited period, liquid water could have mixed with Titan's rich inventory of organic compounds. In that temporary environment, two very different chemical worlds may have met, leaving behind clues that still wait beneath the cold landscape today. A discovery does not always arrive with fanfare. Sometimes it begins as a faint signal buried within a stream of measurements, easy to overlook until its implications unfold. In 2005, as Cassini continued its survey of Saturn's realm, one such signal emerged from a small moon that few expected to become the centerpiece of a profound scientific shift. That moon was Enceladus, with a diameter of only 504 kilometers, which is about 313 miles. Enceladus appears modest beside Saturn's larger companions. Its bright surface reflects an extraordinary amount of sunlight, making it one of the most reflective objects in the solar system. At first glance, it seemed frozen and inactive. The instruments suggested otherwise. During a close flyby, Cassini detected water vapor surrounding the moon. Even that finding was remarkable. Water vapor implied ongoing activity, a process continually replenishing material that should otherwise disperse into space. Scientists immediately wanted a closer look. The second encounter provided it. Cassini passed directly through an enormous plume erupting from the South Polar region. Water, ice, and vapor blasted outward at speeds exceeding 1,400 kilometers per hour, which is about 870 miles per hour. Instead of a dormant ice ball, Enceladus revealed itself as an active world venting material into space. The source soon became visible. Stretching across the South Pole were four major fractures known as tiger stripes. These immense cracks, named Alexandria, Baghdad, Cairo, and Damascus, each extend for roughly 130 kilometers, which is about 81 miles, and reach widths of approximately 2 kilometers, which is about 1.2 miles. From these openings, fresh material escaped continuously. But the most important realization came next. The ejected material was not merely surface frost disturbed by impacts. Analysis showed it originated from liquid water hidden below the icy shell. Beneath the bright exterior lies a global ocean, separated from the surface by ice estimated to be between 16 and 19 miles thick. For the first time, a direct pathway connected an alien ocean to instruments flying overhead. Cassini returned again and again. Over the course of its mission, the spacecraft flew through those plumes 23 separate times. Each passage gathered new chemical clues. The repeated measurements transformed the geysers into natural sampling stations, delivering material from the ocean without requiring a landing or a drill. Then another clue emerged. Scientists identified tiny silica particles within the plume material. Silica forms when water interacts with rock under substantial heat. Laboratory studies indicated temperatures exceeding 90 degrees Celsius or 194 degrees Fahrenheit were necessary to produce the particles observed by Cassini. That finding changed the picture entirely. The ocean was not isolated above a frozen interior. It was touching a rocky seafloor. Water circulated through that rock, absorbed heat, and returned upward, carrying chemical signatures of the interaction. On Earth, similar environments exist around hydrothermal vents, where hot, mineral-rich fluids emerge from the ocean floor. Those vents sustain entire ecosystems without sunlight. For many planetary scientists, that realization elevated Enceladus from an interesting moon to one of the most important places in the search for life beyond Earth. Imagine collecting droplets from an ocean hidden beneath kilometers of ice, then discovering that those droplets carry an inventory astonishingly close to the conditions life requires. That is essentially what Cassini accomplished as it repeatedly crossed through the plumes of Enceladus, turning each passage into an opportunity to sample material originating from a world otherwise sealed from direct exploration. The results accumulated slowly. One measurement confirmed liquid water, another identified dissolved salts. Additional observations revealed particles and gases that pointed toward ongoing geological activity below the frozen crust. With each flyby, the picture became richer and more detailed. The first requirement was already clear. Enceladus possesses a global ocean beneath its icy shell. Current models suggest portions of that ocean may reach depths approaching 10 kilometers, which is about 6.2 miles. Water alone does not create life, but every known living system on Earth depends upon it. Finding a stable reservoir of liquid water immediately elevated the moon's importance. But water is only one ingredient. Life also requires energy. Cassini detected molecular hydrogen emerging from the plumes. The presence of hydrogen indicated an active source, continuously replenishing it. The most likely explanation involves serpentinization, a geological process in which water reacts with certain rocks, generating hydrogen gas as a byproduct. On Earth, microorganisms thrive by exploiting exactly this type of chemical energy. Another box was checked. Organic compounds appeared throughout the sampled material. Organic molecules are carbon-based compounds that serve as the chemical foundation of biology. Cassini detected both simple and complex varieties. Some possessed masses exceeding 200 atomic mass units, suggesting structures considerably more elaborate than the smallest building blocks of organic chemistry. The list continued growing. Nitrogen-bearing compounds appeared in the plume material, including ammonia and more complex organic molecules containing nitrogen. Nitrogen plays a central role in biological systems on Earth, forming essential components of proteins and genetic material. Its presence added another piece to the puzzle. Then came phosphorus. In 2023, researchers re-examining Cassini data identified phosphate within ice grains ejected from the ocean. This marked the first detection of phosphate in an extraterrestrial ocean. Even more striking, estimated concentrations ranged from roughly 100 to 1,000 times higher than those found in Earth's oceans. Phosphorus is a crucial ingredient in biological chemistry, helping store and transfer energy within living cells. But the surprises did not stop there. A study published in Nature Astronomy during October of 2025 revealed an additional collection of complex organic compounds hidden within Cassini's measurements. Scientists identified aliphatic esters, heterocyclic compounds, and several oxygen and nitrogen-bearing molecules. These substances occupy multiple stages along chemical pathways associated with biologically relevant chemistry. Fabian Klenner, of the University of Washington, who led the analysis, summarized the implications carefully. Enceladus appeared to possess all the ingredients required for life as we know it. A distinction remains important. Ingredients are not life itself. Earth's oceans contained water, energy sources, and organic compounds long before biology emerged. Yet when we compare known environments across the solar system, no other location has delivered such a complete inventory through direct sampling. Not Mars, not Europa, not Titan. Enceladus stands alone in that regard. Trace a single grain of ice outward from Enceladus, and its journey does not end at the moon. Instead, it becomes part of something vastly larger, joining a structure that stretches across a significant portion of Saturn's domain. What appears at first to be a local phenomenon gradually reveals itself as a planetary scale process. The tiger stripes never stop supplying material. From the fractures near Enceladus's south pole, Water vapor and ice particles continue streaming into space. Some material falls back onto the moon, some escapes entirely. Yet a substantial fraction enters orbit around Saturn, where gravity takes over and redistributes the particles across an enormous region. Over millions of years, that process has built a ring. Known as the E ring, it occupies the outermost position among Saturn's major rings. Unlike the brighter rings closer to the planet, the E ring is extremely diffuse. Its particles are spread so thinly that the structure remained uncertain until observations during the 1980s confirmed its existence. Its scale is remarkable. The ring extends from near the orbit of Mimas to the orbit of Titan, spanning hundreds of thousands of kilometers across Saturn's system. Even with that immense reach, the particles remain widely dispersed. If you were somehow passing through the E ring, you might scarcely notice it. Yet, from a broader perspective, it forms one of the largest structures associated with the planet. But its origin remained uncertain for years. Scientists suspected Enceladus played a role, though definitive proof required direct investigation. Cassini eventually provided that proof. As the spacecraft moved through regions of the E ring, its instruments sampled the particles themselves and compared their composition with material collected from the plumes. The match was striking. Both environments contained water ice. Both contained sodium salts. Both contained silica particles linked to interactions between water and rock. Both revealed complex organic compounds. The chemical fingerprints aligned so closely that the connection became impossible to dismiss. Suddenly, the ring looked different. Rather than being an isolated feature, the E-ring emerged as a visible extension of processes occurring deep beneath Enceladus's surface. Material erupted from an underground ocean, escaped through fractures in the ice, entered Saturnian orbit, and gradually spread outward into a structure large enough to surround a giant planet. The relationship continues today. Every new particle released from the plumes contributes to the same cycle. Fresh material enters the ring, while older particles are gradually lost through collisions, radiation, and gravitational interactions. The structure persists because the source remains active. But the deeper implication reaches beyond planetary geology. The ocean producing these particles is the same ocean that contains liquid water, chemical energy, phosphorus, nitrogen compounds, and complex organic molecules. The same environment that has attracted attention as a potentially habitable world is also creating part of one of the solar system's most recognizable spectacles. Seen from that perspective, Saturn's beauty becomes connected to something far more intimate. When you look toward the planet and its rings, a portion of what you are seeing originated within a hidden ocean beneath the ice of Enceladus, carried outward grain by grain into space, where it became part of Saturn's enduring halo. Scientific discoveries rarely travel in a straight line. Just when a mystery appears to be narrowing toward an answer, a new piece of evidence arrives and widens the landscape again. That is where the story of Enceladus found itself during September of 2025. For years, the plume material seemed to offer a direct glimpse into the hidden ocean below. Each flyby strengthened the impression that particles erupting from the tiger stripes carried chemical information upward from the subsurface sea. Water, salts, organic compounds, and other ingredients appeared to rise from the depths and spill into space, where spacecraft could sample them directly. But another possibility emerged. Researchers associated with Europlanet published experimental results suggesting that some organic compounds might form much closer to the surface than previously assumed. Their work focused on Saturn's magnetosphere, the immense magnetic environment surrounding the planet and extending across its system of moons. That environment is far from passive. Charged particles trapped within Saturn's magnetic field continually bombard Enceladus. Over time, radiation interacts with surface ice and frozen chemicals, driving reactions that can assemble increasingly complex compounds. This process, known as radiation chemistry, uses energetic particles to transform simple materials into more elaborate molecular structures. The implications are significant. If radiation chemistry is producing organics on the surface, then some fraction of the molecules detected in the plumes may not originate in the ocean at all. Instead, they could form near the exterior, become incorporated into erupting material, and eventually reach spacecraft instruments. A difficult question follows. When Cassini detected complex organic compounds, how many came from the hidden ocean and how many were manufactured later by surface processes? At present, no definitive answer exists. The available measurements cannot separate those contributions with complete confidence, but uncertainty cuts in both directions. Surface chemistry could potentially make the ocean appear richer than it really is. It could also obscure important signatures originating below. The resulting picture may either exaggerate or conceal aspects of Enceladus's biological potential. Researchers must now consider both possibilities. Cassini was never designed to resolve that distinction fully. Its instruments achieved extraordinary results, yet they operated under strict limitations of size, power, and technology. Determining the precise origin of complex molecules requires laboratory capabilities far beyond what could be carried aboard the spacecraft. Researchers need measurements of isotopes, molecular structures, and chemical relationships at levels of precision unavailable during the mission. That need is shaping future plans. One of the strongest motivations for a new Enceladus mission is the desire to collect plume material and analyze it with far greater sophistication. Ideally, samples would be returned to Earth, where entire laboratories could be devoted to the task. Such investigations could reveal whether detected compounds formed in an ocean, on an icy surface, or through a combination of both pathways. The interest is growing. In 2024, the European Space Agency identified Enceladus as a leading candidate for future exploration of the outer solar system. Studies have already examined concepts involving landers and advanced sampling systems near the south polar terrain. But for now, the plumes remain interpreters whose reliability has not been fully tested. They continue to carry clues from a hidden world, while leaving open the possibility that some of those clues were rewritten during the journey. Some mysteries emerge from discovering something unexpected. Others appear when everything seems known, yet the numbers refuse to agree. Enceladus belongs to the second category. The moon reveals oceans, plumes, and active geology, but beneath all those discoveries lies a deeper problem. The energy powering this activity appears greater than scientists can comfortably explain. At first glance, Enceladus should be simple. Its diameter measures only 504 kilometers, which is about 313 miles. A world this small possesses relatively weak gravity and a limited internal reservoir of heat. Planetary bodies of comparable size generally cool quickly after formation. Their interiors solidify, geological activity fades, oceans freeze. That expectation works well elsewhere. Yet Enceladus refuses to cooperate. Beneath its icy crust exists a global ocean. Water erupts through fractures into space. Heat escapes from the interior continuously. Every observation points toward a moon that remains active despite possessing characteristics that should have led to long-term dormancy billions of years ago. Scientists do have an explanation. The leading mechanism is tidal heating. Tidal heating occurs when gravity repeatedly flexes a celestial body, converting mechanical stress into heat. Enceladus follows a slightly elliptical orbit around Saturn. As the distance between moon and planet changes, Saturn's gravitational pull changes as well. The interior stretches and relaxes over and over again, like kneading dough. Each cycle generates friction within rock and ice. Over immense periods of time, that friction becomes a powerful energy source. Tidal heating is widely accepted as a major contributor to the warmth observed beneath the surface. But calculations revealed a problem. When researchers estimated how much energy tidal heating should produce, the results repeatedly fell short of the observed heat output. The difference was not trivial. Models struggled to generate enough energy to sustain the ocean and drive the level of activity recorded by Cassini. The discrepancy persisted. Then another complication appeared. Analysis released during November of 2025 indicated that significant heat was escaping from the North Polar region as well. Earlier attention had focused largely on the South Pole because of the spectacular plume activity there. The new findings suggested a more widespread energy source operating within the moon. That was unexpected. Traditional tidal heating models often concentrate energy near equatorial regions rather than distributing substantial amounts toward both poles. The observed pattern did not align neatly with standard predictions. Once again, Enceladus appeared more energetic than theory anticipated. Researchers began looking deeper. One promising possibility involves the ocean floor itself. Evidence already suggests water circulates through a rocky interior containing hydrothermal systems. Chemical reactions associated with serpentinization may release additional energy as water interacts with certain minerals. These reactions are already considered important for generating hydrogen. They may also contribute meaningful amounts of heat, but the exact contribution remains uncertain. No current model fully accounts for every observation. Tidal forces clearly matter. Hydrothermal processes may matter as well. Additional mechanisms could still be waiting to be identified. For now, the accounting remains incomplete. Enceladus continues to emit more energy than known sources comfortably explain. In planetary science, few things attract attention faster than a world whose heat budget refuses to balance. Long before the mission ended, its final destination had already become a subject of careful debate. Engineers, planetary scientists, and mission planners understood that Cassini could not orbit Saturn forever. Every maneuver consumed propellant. Every correction reduced the remaining margin. By early 2017, the spacecraft had reached the point where choices could no longer be postponed. The situation created an unusual dilemma. Cassini was still healthy. Its instruments continued producing valuable science, yet eventually it would lose the ability to control its trajectory. Left alone, the spacecraft would drift unpredictably through Saturn's system, guided only by gravity and chance. That possibility carried consequences. Among Saturn's moons are worlds increasingly viewed as potential habitats for life. Enceladus contains a global ocean beneath its ice. Titan possesses complex organic chemistry, unlike anything else in the solar system. Future missions may search those environments for evidence of biology. Any contamination from Earth could complicate that search forever. Scientists took the concerns seriously. Although spacecraft are carefully sterilized before launch, absolute removal of terrestrial microorganisms is impossible. Some organisms on Earth survive astonishing extremes. If even a tiny number endured the journey and eventually reached a habitable environment, future discoveries could become difficult to interpret. The mission therefore faced a difficult requirement. Cassini needed to be destroyed. But before the final descent, researchers designed one last campaign capable of transforming the spacecraft's remaining months into one of the most productive periods of the entire mission. The result became known as the grand finale. Its path was extraordinary. Cassini would repeatedly dive through the narrow gap, separating Saturn's innermost ring from the upper atmosphere. That corridor measured roughly 2,000 kilometers wide, which is about 1,243 miles. No spacecraft had ever explored that region directly. Scientists possessed only limited knowledge of what waited inside. There was genuine uncertainty. Tiny particles moving at enormous speeds could damage instruments or cripple the spacecraft entirely. Researchers could estimate the risk, but no calculation could replace direct experience. The only way to know was to fly through the gap. Again and again, Cassini completed all 22 planned passes successfully. During those crossings, it gathered unprecedented measurements of Saturn's gravity field, magnetic field, and ring environment. Information collected during the grand finale continues to support scientific studies years after the mission ended. Then came the final orbit. On September 15th, 2017, Cassini entered Saturn's atmosphere, traveling at approximately 113,000 kilometers per hour, which is about 70,215 miles per hour. Atmospheric drag steadily increased. The spacecraft responded by firing its thrusters, struggling to maintain the orientation required to keep its antenna pointed toward Earth. For 91 seconds, the transmission continued. Data streamed across the vast distance separating Saturn from our world. Engineers monitored the signal while the atmosphere grew denser around the spacecraft. Eventually, the thrusters could no longer compensate. Control was lost. The antenna drifted away from Earth. Then the signal vanished. No wreckage remains in orbit. No frozen relic circles Saturn today. The spacecraft that revealed hidden oceans, impossible storms, and active worlds became part of the planet it spent more than a decade exploring, its final measurements arriving during the last moments of its existence. As Cassini threaded repeatedly through the space between Saturn and its rings, the spacecraft was doing more than completing a dramatic farewell. During each close passage, it was measuring tiny changes in motion, subtle accelerations caused by gravity itself. Those measurements would eventually reveal details hidden far below the cloud tops, in regions no telescope could ever observe directly. Gravity became a probe. Every massive object exerts a gravitational pull. By tracking Cassini's motion with extraordinary precision, scientists could determine how Saturn's mass was distributed throughout its interior. Small deviations in the spacecraft's trajectory carried information about structures buried tens of thousands of kilometers beneath the visible atmosphere. The results challenged long-standing assumptions. For decades, many models pictured Saturn as a relatively orderly system. A dense rocky core occupied the center. Layers of different materials surrounded it in distinct shells. The arrangement appeared neat and predictable, but Saturn turned out to be messier. Grand finale data pointed toward what researchers call a fuzzy core. A fuzzy core is a broad region where rock, ice, and gas blend together gradually instead of remaining separated into sharply defined layers. Rather than forming a compact central object, Heavy materials appear mixed through a substantial fraction of the planet's interior. The scale was surprising. Current estimates suggest this diffuse region extends across roughly 60% of Saturn's radius. That is vastly larger than earlier predictions. Deep inside the planet, boundaries that once seemed clear may not exist at all. Instead, composition changes gradually with depth, creating a transition zone of enormous size. But gravity was only part of the story. The grand finale also provided some of the most precise measurements ever obtained of Saturn's magnetic field. Planetary magnetic fields are generated by electrically conducting material moving within an interior. Those motions typically produce fields tilted at least slightly away from the planet's rotation axis. Earth behaves that way. So do the other magnetized planets. Each possesses a measurable offset between its magnetic field and its rotational orientation. The differences vary, but they exist. Saturn stands apart. Measurements indicated that Saturn's magnetic field aligns with its rotation axis to within less than 6/100ths of a degree. The symmetry is extraordinary. According to many theoretical models, such perfect alignment should be difficult to maintain over geological timescales. Small disturbances should gradually introduce asymmetries. Yet, the alignment persists. Researchers continue refining explanations, searching for interior processes capable of generating such an unusually balanced magnetic structure. Once again, Saturn proved less cooperative than theory expected. The rings added another surprise. Close observations during the grand finale allowed scientists to estimate their mass more accurately than before. The results suggested the entire ring system contains roughly the same mass as the moon Mimas. Compared with earlier assumptions, the rings appeared lighter and younger. That finding connected directly to another discovery. Measurements of ring rain showed material continually falling from the rings into Saturn's atmosphere. Combined with the lower estimated mass, those observations strengthened the conclusion that the rings are temporary structures on astronomical timescales. The grand finale, therefore, revealed something remarkable. Saturn's interior is more complex than expected, its magnetic field more mysterious than predicted, and its most iconic feature less permanent than generations once imagined. Few mysteries are more unsettling to scientists than uncertainty surrounding something fundamental. After decades of exploration, detailed observations, and sophisticated models, Saturn still seemed unwilling to answer a remarkably simple question. How long does the planet take to complete a single rotation? For most worlds, the answer is straightforward. A rocky planet provides landmarks. Mountains, craters, and other surface features rotate into view repeatedly, allowing astronomers to measure the spin rate directly. Each rotation leaves a visible signature. Saturn offers no such convenience. What we observe are clouds suspended within a deep atmosphere. Different cloud bands move at different speeds. Winds race around the planet. Features appear, evolve, and disappear. Nothing provides a permanent marker connected to the deep interior. Scientists needed another method. They turned to radio emissions generated through interactions involving Saturn's magnetic field. These repeating bursts acted like a planetary clock. By measuring the interval between signals, researchers could estimate the rotation rate hidden beneath the visible atmosphere. For a time, the approach seemed reliable. Then observations from the Voyager missions during the early 1980s were compared with measurements collected decades later by Cassini. Something unexpected appeared. The radio period had shifted by several minutes. That should not happen. Planets do not meaningfully alter their rotation rates over such short intervals. A world the size of Saturn possesses enormous angular momentum, which is a measure of rotational motion that strongly resists change. Yet the radio signals implied exactly that. The contradiction lingered. Researchers debated whether Saturn's interior behaved differently from any known planet. Perhaps deeper layers rotated independently from upper regions. Perhaps unknown processes were affecting the magnetic field itself. Proposed explanations multiplied while definitive answers remained elusive. The puzzle persisted for decades, but resolution arrived from an unexpected direction. Observations associated with the James Webb Space Telescope contributed to a study published during June of 2026. Rather than revealing a changing planetary rotation rate, the research pointed toward a misunderstanding of the radio signals themselves. Saturn had been spinning steadily all along. The varying radio period originated much higher in the atmosphere than previously recognized. Specifically, the effect involved the ionosphere, a region where gases become electrically charged through interactions with solar radiation and energetic particles. Activity there proved crucial. Researchers found that auroras near Saturn's northern polar regions heat portions of the ionosphere. That heating generates powerful winds. Those winds influence electrical currents flowing through the upper atmosphere. The currents then contribute energy back into the auroral system itself. A feedback loop emerges. As conditions within that system evolve, the timing of associated radio emissions shifts as well. The signals appear to speed up or slow down, even though the planet's deep interior continues rotating at the same rate. The mystery suddenly looked different. For more than 40 years, scientists had been interpreting changes in a clock whose hands were moving independently of the mechanism they hoped to measure. The radio emissions remained valuable, but they were responding to atmospheric processes rather than directly reporting Saturn's true rotation. What seemed like evidence of an impossible planetary behavior ultimately became a lesson in atmospheric complexity. Saturn was never changing its spin. Instead, its upper atmosphere had spent decades disguising the answer, hiding a stable reality beneath layers of electrical activity, auroral energy, and moving winds. Light is usually the final step in a process. We see a glow, trace it back to its source, and discover the mechanism responsible for producing it. Saturn's auroras seem to follow that familiar pattern for many years. Charged particles arrived, atmospheric gases responded, and luminous rings appeared around the poles. The story appeared complete. Observations from the Hubble Space Telescope and Cassini revealed immense auroral displays encircling both polar regions. Although invisible to human eyes in their strongest wavelengths, these glowing structures shone brightly in ultraviolet light, outlining areas where energetic particles interacted with the upper atmosphere. The explanation felt familiar. On Earth, auroras occur when charged particles carried by the solar wind travel along magnetic field lines and collide with atmospheric gases. Those collisions transfer energy and produce light. The process is complex, but the overall chain of events is well understood. Saturn seemed similar, but detailed observations associated with the James Webb Space Telescope revealed something more intricate unfolding above the cloud tops. The auroras were participating in a process far more active than scientists had previously confirmed within a planetary atmosphere. The glow was influencing its own environment. Researchers discovered that auroral activity heats portions of Saturn's ionosphere. The ionosphere is a region of the upper atmosphere containing electrically charged particles. Heating does not occur uniformly across the entire region. Some areas become warmer than others, creating differences in temperature across vast distances. Those differences matter. Whenever temperature contrasts develop, atmospheric circulation tends to follow. Warm regions and cooler regions drive movement. Winds emerge as energy redistributes itself through the atmosphere. At Saturn, those winds become electrically important. As charged particles move through the ionosphere, they interact with magnetic field lines and generate electrical currents. The currents flow through portions of the atmosphere and magnetosphere, transferring energy through the system. Then, something remarkable happens. Those currents contribute to the production of additional auroral activity. More aurora generates more heating. Additional heating strengthens atmospheric circulation. Stronger circulation influences electrical currents. The cycle repeats. A feedback loop emerges. The aurora is no longer simply the end result of incoming energy. It becomes an active participant in sustaining and amplifying the process that created it. External energy from the sun remains necessary. Without that input, the system would not operate. Yet once initiated, the cycle enhances itself through interconnected atmospheric and electromagnetic processes. The effect is substantial. Researchers now believe this mechanism helps explain auroral intensities greater than solar input alone would predict. Saturn's atmosphere is not merely responding to conditions imposed from outside. It is modifying those conditions internally and feeding energy back into the system. But another mystery remains. The northern and southern auroras do not behave as perfect mirror images. Differences persist between the two poles, even though they are connected through the same planetary magnetic environment. Scientists continue investigating the source of that asymmetry. The pattern feels strangely familiar. At one pole, Saturn displays the extraordinary hexagonal circulation discussed earlier. At the other, a hurricane-like vortex dominates. Now, the auroras show differences as well. Once again, the planet resists simple symmetry. Even its polar lights reveal a world where matching conditions often evolve into remarkably different outcomes, driven by processes still being unraveled today. Some worlds seem determined to ignore expectations. After spending years studying Saturn's major moons, scientists discovered that several smaller members of the system behaved in ways that did not fit familiar categories. Their shapes, motions, and appearances were so unusual that entirely new explanations became necessary. Pan was among the first surprises. Orbiting within a gap inside Saturn's rings, this small moon measures roughly 28 kilometers in diameter, which is about 17 miles. At first glance, one might expect a simple rounded object shaped by gravity. Instead, Pan resembles a flattened flying saucer suspended in space. Atlas displays a similar appearance. Both moons possess enormous equatorial ridges extending outward around their midsections. The ridges create a distinct profile, unlike anything previously encountered in planetary science. Their silhouettes appear almost artificial, as though an enormous belt had been wrapped around each body. The explanation emerged gradually. Over millions of years, ring particles accumulated along the moon's equators. Material orbiting nearby moved slowly enough to settle onto the surface rather than escaping into space. Layer by layer, the deposits grew larger. What began as modest accumulations eventually became permanent geological structures. The rings reshaped the moons. Rather than merely orbiting within Saturn's ring system, Pan and Atlas became products of it. Their present forms preserve a visible record of long interactions between small worlds and countless orbiting particles. But Saturn's collection of oddities extends much further. Consider Hyperion. Its appearance has often been compared to a sponge because the surface is covered with deep cavities, pits, and depressions. Unlike many moons shaped into spheres by their own gravity, Hyperion remains irregular and lumpy. Even more remarkable, its density is lower than that of water, suggesting a highly porous interior filled with substantial empty space. Then there is its motion. Most moons rotate predictably. Their orientation changes in regular ways that can be calculated far into the future. Hyperion refuses such order. It tumbles through space in a state known as chaotic rotation, where gravitational influences continuously alter its spin. No stable pattern emerges. A traveler standing on Hyperion would experience an unpredictable cycle of illumination. Sunrise and sunset would not follow a reliable schedule. The moon's orientation shifts too erratically for that. Yet another mystery waits farther out. Iapetus has puzzled astronomers since its discovery in 1671 by Giovanni Domenico Cassini. One hemisphere shines brightly, reflecting sunlight like fresh snow. The opposite hemisphere appears dramatically darker, creating one of the most striking contrasts found anywhere in the solar system. The difference is extreme. Researchers believe a process called thermal segregation contributes to the pattern. Thermal segregation occurs when darker regions absorb more sunlight and become warmer. Ice then migrates away from those warmer locations and accumulates in cooler areas. Over long periods, dark regions grow darker while bright regions become brighter. But a question remains unresolved. Where did the original dark material come from? Scientists continue debating the answer. Some evidence points toward external sources. Other possibilities involve processes occurring directly on the moon. Like many of Saturn's most intriguing worlds, Iapetus still withholds part of its story, reminding us that even after centuries of observation, the system remains filled with enduring mysteries. Far from the grand scale of planets and major moons, some of Saturn's most remarkable architects are barely large enough to deserve notice at first glance. Yet as we drift deeper into the ring system, we find tiny worlds exerting influence far beyond their size, shaping structures that stretch across enormous distances and maintaining patterns that seem almost impossible to preserve. These are the shepherd moons. Their name reflects their role. Like herders guiding a scattered flock, they use gravity to organize countless ring particles into narrow bands, sharp boundaries, and intricate formations. Without them, many of Saturn's rings would gradually spread outward, becoming broader and less defined over time. The most striking example lies within the delicate F ring. Unlike the broad luminous bands that dominate Saturn's appearance, the F ring is slender and restless. On either side travel two small moons named Prometheus and Pandora. Together they create a gravitational partnership that continuously sculpts the ring's structure. Prometheus is especially disruptive. As it passes near the ring, its gravity reaches into the surrounding particles and pulls streams of material away from the main ring. These temporary extensions stretch outward like elongated strands before gradually dispersing. When viewed over time, the ring develops braided and twisted patterns that seem almost woven by an unseen hand. Nothing remains fixed. Each encounter slightly alters the arrangement of particles. Small differences accumulate. A minor disturbance can grow into a dramatically different structure only weeks later. The system became so sensitive to changing conditions that Cassini researchers described aspects of its behavior as unpredictable, a rare word in a field built upon mathematical precision. But Prometheus does more than reshape the ring. During particularly close approaches, it removes material from the ring itself. Dark channels appear where particles have been displaced. These gaps widen, evolve, and eventually fade as orbital motion redistributes matter. For the first time, scientists observed direct evidence of a moon actively eroding a planetary ring while simultaneously helping define its structure. The deeper we look, the stranger the situation becomes. The outer boundaries of Saturn's B ring are astonishingly sharp. This ring is the densest component of the entire system, yet some of its edges transition from crowded particles to comparative emptiness with remarkable abruptness. Standard orbital models struggle to explain how such precision can persist over long timescales. One obvious explanation would involve additional shepherd moons, but none have been found. Extensive observations by Cassini revealed no large bodies occupying the positions where many researchers expected them to exist. The missing shepherds created a new puzzle. If no visible moons are maintaining these boundaries, what is? A leading possibility points toward hidden moonlets embedded within the rings themselves. Moonlets are tiny natural satellites, far smaller than conventional moons, whose local gravitational influence may be sufficient to sculpt nearby particles. Countless such bodies could exist beneath the limits of present observations, but certainty remains out of reach. The structures they may create are visible, the objects responsible are not. Within Saturn's rings, gravity continues drawing lines with extraordinary precision, while the sculptors themselves remain concealed among the particles they shape. Time behaves differently on Titan. While seasons on Earth arrive and depart within a single year, Saturn's largest moon moves through a much slower rhythm. One complete journey around the Sun takes nearly 30 Earth years, meaning each season lingers for roughly 7.5 Earth years. During the long span of the Cassini mission, we were fortunate enough to witness one of these transitions unfold in real time. At first, the changes appeared gradual. Titan shifted from southern summer toward northern summer, and scientists expected the atmosphere to respond. Seasonal behavior had already been predicted, but as observations accumulated over successive flybys, the moon began revealing patterns far more dynamic than many models anticipated. The southern hemisphere entered winter. Soon afterward, a massive vortex formed above the South Pole. A vortex is a rotating atmospheric circulation similar in principle to a cyclone, though operating under very different conditions. This polar storm expanded through Titan's upper atmosphere and drew chemical compounds downward from higher altitudes. New substances appeared. Among them was dicyanoacetylene, an exotic molecule rarely encountered outside laboratory environments on Earth. Yet, on Titan, it accumulated naturally in sufficient quantities to help form a distinct cloud layer. What seemed improbable under terrestrial conditions emerged as part of an ordinary seasonal process on this distant moon. The transformation happened rapidly. Researchers found that chemical reactions were proceeding faster than expected in an environment averaging about 179 degrees Celsius below zero, or 290 degrees Fahrenheit below zero. Existing atmospheric models struggled to reproduce the observed pace of change. The discrepancy was large enough to prompt a re-evaluation of how chemistry behaves under Titan's extreme conditions. But chemistry was only part of the story. Deep within the moon's methane clouds, Cassini detected electromagnetic signatures that resembled lightning activity. The evidence remained indirect. Scientists chose their conclusions carefully and stopped short of claiming a definitive detection. Even so, The signals hinted that energetic weather processes might be occurring beneath Titan's hazy skies. You can imagine the scene. Cloud systems drift across a world where methane plays a role similar to water on Earth. Methane evaporates, forms clouds, falls as rain, and collects in lakes and seas. Entire weather cycles operate using compounds that would freeze solid in most places familiar to us. But this remarkable system contains a deeper puzzle. Sunlight gradually breaks apart methane molecules in Titan's atmosphere. Over spans of tens of millions of years, that process should steadily deplete the moon's methane reserves. Left unchecked, the atmosphere would evolve into something very different from what we observe today. Yet, Titan remains rich in methane. Something must be replacing what sunlight removes. Scientists have proposed several possibilities. Methane may emerge from the interior through geological activity. Reservoirs trapped beneath the surface could slowly leak upward. Other mechanisms have also been considered. None have been confirmed. As the seasons advanced and the atmosphere transformed before our eyes, Cassini revealed a moon that was active, evolving, and chemically restless. Titan's weather was not simply an alien version of familiar meteorology. It was evidence that an entirely different planetary system of climate and chemistry could remain vibrant across immense stretches of time, sustained by processes that we still do not fully understand. Imagine lowering yourself through Saturn's clouds, descending layer after layer into a world that appears immense and substantial from afar. The deeper you travel, the stranger the experience becomes. Beneath the storms, beneath the bands, beneath every familiar image of the ringed planet, you encounter a surprising reality. Saturn is, in many ways, a planet built from emptiness. Its density reveals the first clue. Among all the planets in the solar system, Saturn is the least dense. On average, each cubic centimeter of Saturn contains only about 0.687 grams of matter. Water contains 1 gram in the same volume. Put another way, Saturn is roughly 31% less dense than water itself. The comparison sounds impossible. If an ocean existed large enough to contain the entire planet, Saturn would float. Of course, no such ocean could exist. The planet spans nearly 120,000 kilometers across, which is about 74,565 miles. Yet the comparison captures an important truth. Saturn contains far less matter than its enormous size suggests. Most of that volume consists of hydrogen and helium. These are the lightest elements known. Near the upper atmosphere, hydrogen exists primarily as a gas. As you descend, gravity steadily compresses the material. The pressure rises. The density increases. Gas gradually transitions into forms that behave more like liquid than atmosphere. The transformation continues. Far below the visible clouds, conditions become so extreme that hydrogen enters an exotic phase known as metallic hydrogen. Metallic hydrogen is hydrogen compressed so intensely that its electrons move freely between atoms. In ordinary materials, that behavior is associated with metals, which is why the name was chosen. This changes everything. A fluid capable of conducting electricity can generate magnetic fields when it moves. Saturn rotates rapidly, completing one spin in a little over 10 hours. As vast currents of metallic hydrogen circulate through the interior, they create the powerful magnetic field surrounding the planet. But metallic hydrogen remains deeply mysterious. Scientists have attempted to create it on Earth using intense compression produced by advanced laboratory equipment and powerful laser systems. The material appears only briefly, surviving for tiny fractions of a second before conditions collapse. Inside Saturn, however, Metallic hydrogen has persisted for roughly 4.5 billion years. The deeper we descend, the less distinct the planet becomes. For decades, many models pictured Saturn as a series of neat layers with gases above and a clearly defined core below. Data collected during the final close passes of the Cassini mission challenged that picture. Measurements of the gravitational field suggested something far less orderly. The center appears blurred. Rather than encountering a sharp boundary separating core and envelope, scientists found evidence for a diffuse mixture of rock, ice, and compressed gases extending outward through more than half the planet's radius. Material gradually changes composition instead of forming clean divisions. But perhaps that is fitting. The farther we probe Saturn, the more it resists simple categories. What seems solid becomes fluid. What appears empty contains immense complexity. Even the planet's deepest interior refuses to separate itself into tidy layers, remaining a vast transition between states rather than a place where one thing clearly ends and another begins. There are moments in planetary science when distance stops being the hardest concept to grasp. Instead, the challenge becomes time. Saturn asks us to stretch our sense of duration so far that familiar scales begin to lose meaning. As we gather the discoveries left behind by decades of exploration, we find ourselves confronting a world whose story unfolds across spans almost impossible to hold in a single thought. The beginning reaches far back. Saturn formed approximately 4,503,000,000 years ago during the earliest stages of solar system history. At that time, vast clouds of gas and dust were collapsing under gravity, gradually assembling the planets we know today. The young Saturn emerged within roughly the first 10 million years of that process, long before Earth had oceans, continents, or life. For most of that immense history, the planet may have looked very different. Evidence gathered during recent decades suggests Saturn's rings are surprisingly young. Current estimates place their formation somewhere between 10 million and 100 million years ago. In cosmic terms, that is remarkably recent. A moon, comet, or other icy body likely wandered too close to Saturn and crossed a critical boundary where tidal forces overwhelmed its internal strength. The object came apart. Fragments spread around the planet and gradually settled into the flattened structure we recognize today. The rings that seem timeless may actually be newcomers, appearing only during the final fraction of Saturn's existence. Consider what that means. Dinosaurs first appeared on Earth roughly 230 million years ago. If the higher estimates for ring age are correct, Saturn's rings may already have existed when those first dinosaurs walked across ancient landscapes. They would have remained in orbit throughout the rise of giant reptiles, the impact that ended their dominance, the emergence of mammals, and eventually the appearance of our own species. Yet even the rings are temporary. Measurements collected during the final years of the Cassini mission revealed that ring material is gradually falling into Saturn. Ice particles drift inward, dust follows. Over geological timescales, the process is surprisingly efficient. The rings are losing mass, and current estimates suggest they may already be living through the later stages of their history. But elsewhere in the system, other processes appear astonishingly persistent. Enceladus continues venting material from beneath its icy crust. Its ocean remains in contact with rock. Hydrothermal activity may still be operating on the sea floor. Organic compounds continue moving through a hidden environment that has potentially existed for billions of years. The scale is difficult to absorb, For spans longer than the entire history of complex life on Earth, chemical reactions may have been unfolding beneath that frozen surface. Water has circulated, minerals have interacted, energy has flowed through the system again and again. And throughout those immense ages, no observer was required. The ocean existed before telescopes, before civilizations, before humanity itself. Whether anything emerged from that chemistry remains unknown. We can identify ingredients. We can trace energy sources. We can measure oceans and plumes. But after billions of years, the most profound question still waits for an answer, and Saturn's system continues keeping it. Some endings are caused by failure. Others arrive through necessity. As the final chapter of the Cassini mission approached, the people responsible for the spacecraft faced a decision unlike any they had encountered during decades of exploration. The question was no longer what discoveries remained to be made. The question was how to protect discoveries that had not yet happened. By the year 2017, Cassini had spent 13 years orbiting Saturn and more than 20 years traveling through space since launch. Its supply of propellant was steadily diminishing. Without enough fuel to control its trajectory indefinitely, a future loss of guidance became unavoidable. Eventually, the spacecraft would drift. That prospect created a serious concern. During its years in the Saturn system, Cassini had transformed our understanding of moons such as Titan and Enceladus. Both worlds now appeared capable of supporting environments relevant to the study of life. If the spacecraft were left uncontrolled and later crashed into one of them, even an extremely remote possibility of biological contamination had to be considered. The stakes were unusual. Planetary protection policies, established through international agreements and guided by the Committee on Space Research, exist to preserve the scientific integrity of potentially habitable worlds. The principle is straightforward. If life is ever discovered elsewhere, researchers must be confident it originated there and was not accidentally delivered from Earth. Cassini presented a dilemma. The spacecraft had not undergone the sterilization procedures that would have been required for an intentional impact on Enceladus or Titan. Those standards had not been necessary when the mission launched. Many of the most important discoveries about these moons occurred years later. Success changed everything. The very observations that revealed Enceladus as a compelling environment for astrobiology also eliminated the possibility of allowing Cassini to remain in the Saturn system indefinitely. The spacecraft that uncovered evidence for a potentially habitable ocean had to be prevented from ever reaching that ocean. But the responsibility fell upon people who knew Cassini best. Engineers, navigators, scientists, and mission planners had spent years guiding every maneuver. They had celebrated successful flybys, responded to unexpected challenges, and watched the spacecraft return discoveries that reshaped planetary science. For them, the final trajectory was not an abstract calculation. It was personal. The solution became the grand finale, a sequence that ultimately directed Cassini into Saturn's atmosphere on the 15th of September, 2017. There, during its final descent, the spacecraft continued transmitting scientific measurements. Even while atmospheric forces began tearing it apart, instruments remained active, gathering information about Saturn's composition until communication ended. The flow of data stopped. Yet the mission did not simply conclude. Some of the measurements collected during those last moments continue informing scientific studies today. Researchers still examine information returned during the descent, extracting details that were impossible to obtain in any other way. And something else happened as well. The spacecraft ceased to exist as a machine, but its material remained. The metals, composites, electronics, and structures that once crossed billions of kilometers, which is about 1,864,000,000 miles, became part of Saturn itself. Mixed into the planet's hydrogen and helium, those atoms now share the environment Cassini spent 13 years exploring, completing a journey that ended within the world it came to know best. A curious feature of exploration is that discoveries rarely bring closure. More often, they create better questions. By the time the Cassini mission ended, Saturn had become less understood in many ways than when the spacecraft first arrived. Oceans had appeared beneath ice, atmospheric mysteries had deepened, entire categories of potential habitats had emerged. The end of one mission became the beginning of several others. The journey is continuing. Among the most ambitious projects now planned is Dragonfly, a nuclear-powered rotorcraft designed to explore Titan directly. Unlike traditional landers that remain fixed in one location, Dragonfly will fly from site to site across the moon's surface. Current plans call for launch in the year 2028, followed by arrival in 2034. Its range is remarkable. Over the course of the mission, Dragonfly is expected to travel hundreds of kilometers, which is about hundreds of miles, examining landscapes shaped by complex organic chemistry. Instruments aboard the craft will analyze surface materials, atmospheric compounds, and geological features in an environment unlike any other known world. But Titan is only part of the story. Interest in Enceladus has continued to grow as evidence for its subsurface ocean has accumulated. The European Space Agency identified Enceladus as a priority target within its Voyage 2050 science program, placing the Moon among the leading candidates for future exploration. Detailed mission studies are already underway. The goal is straightforward. Scientists want direct access to material emerging from beneath the ice. Every plume particle carries information from an ocean hidden far below the surface. Sampling those particles with more advanced instruments could reveal details that Cassini was never designed to detect. Another proposal pushes even further. A concept known as the Enceladus Orbilander would first orbit the Moon for approximately 18 months before descending to the surface. The mission design includes instruments capable of analyzing organic chemistry at unprecedented levels of detail. The capabilities are extraordinary. One instrument would function as an advanced mass spectrometer capable of identifying individual amino acids. Amino acids are molecular building blocks used by life on Earth to construct proteins. Another instrument would operate as a microscope designed to examine structures at cellular scales. A third system would search for complex biological polymers, large molecules associated with living processes. But none of these missions begins with certainty. Each has been shaped by the same challenge. Cassini revealed environments that appear potentially habitable, yet it lacked the tools needed to determine whether biology is actually present. The next generation of spacecraft has therefore been designed around a single objective. Finding evidence is one thing, interpreting evidence is another. If signs of life exist in the outer solar system, the first indication may emerge as an unusual pattern within a dataset. Perhaps a recurring chemical ratio, perhaps a molecular distribution that resists conventional explanation, perhaps multiple observations pointing toward the same conclusion from different directions. The answer may arrive gradually, and many of the scientists developing these missions understand a sobering reality. Space exploration unfolds across decades. Some researchers contributing today may never witness the final result. Yet they continue anyway, building instruments, refining designs, and extending the search farther outward, trusting that future generations will carry the question the rest of the way. Consider the proportion for a moment. Everything we have explored together, every plume, every ring, every storm, every unanswered puzzle, emerged from a single spacecraft, spending 13 years around one world. That is a remarkably small sample. Cassini arrived at Saturn and transformed our understanding of an entire planetary system. Yet Saturn itself is only one planet among the 8 major planets orbiting our star. Beyond that lies a scale that steadily slips beyond ordinary intuition. The numbers grow quickly. Our solar system occupies a modest corner of the Milky Way galaxy. Current estimates suggest that this galaxy alone contains somewhere between 100 billion and 400 billion star systems. Beyond the Milky Way galaxy, observations indicate that the observable universe contains roughly 2 trillion galaxies. We are surrounded by abundance. Against that backdrop, the achievements of Cassini become even more striking. During just 13 years of sustained observation, the mission turned a familiar textbook planet into a source of mysteries that continue multiplying long after the spacecraft itself disappeared. Several remain unresolved. The Great Northern Hexagon still lacks a fully confirmed explanation. A second hexagonal pattern, discovered deeper within the atmosphere, remains unexplained as well. Saturn radiates more internal heat than many models predict. Enceladus releases more energy than expected from known heating mechanisms. Ring spokes emerge and fade without a trigger scientists can consistently forecast. Measurements from the grand finale altered assumptions about the rings, suggesting an age and mass very different from previous expectations. But uncertainty is not a defect. When observations disagree with predictions, science does not regard that as failure. Instead, it treats the discrepancy as information. Each unanswered question reveals a place where reality contains details our current understanding has not yet captured. That process has repeated throughout history. Improved instruments uncover unexpected behavior. Unexpected behavior forces new theories. New theories generate fresh predictions. Those predictions lead to further observations. Knowledge advances through revision rather than completion. Saturn offers a vivid example. A mission originally designed to study a ringed giant instead revealed ocean worlds, active chemistry, hidden energy sources, and environments that expanded the modern search for life. The deeper researchers looked, the larger the unknown became. Carl Sagan understood that pattern well. In 1994, reflecting on exploration, he wrote that somewhere, something incredible is waiting to be known. At the time, many of Saturn's most surprising discoveries remained hidden. The oceans of Enceladus had not yet been confirmed. The complexity of Titan's chemistry had not been fully revealed. The strange behavior of the rings still waited in the future. But discovery often unfolds slowly. Organic chemistry findings from Enceladus, published in 2025, emerged more than 28 years after Cassini launched from Earth. Some of the data had been gathered long before many of the scientists now studying it completed secondary school. The spacecraft is gone. Its observations remain. And as you consider the vastness beyond Saturn, it becomes difficult to escape a simple realization. If one mission around one planet uncovered this much complexity, what waits within the countless worlds still untouched by human investigation? Far beyond the familiar warmth of Earth, Enceladus continues its orbit around Saturn, carrying within it a hidden ocean beneath a shell of ice. The distance separating that ocean from us is immense. roughly 1,200,000,000 kilometers, which is about 746 million miles. Yet distance alone does little to diminish the significance of what may exist there. Beneath the frozen surface, water remains in contact with rock. That detail matters. When water interacts with a rocky seafloor over immense stretches of time, chemistry becomes active. Minerals dissolve, energy is exchanged, new compounds form. On Enceladus, evidence gathered from the great plumes suggests this process has been unfolding for an extraordinarily long period. The ingredients appear familiar. Liquid water has been detected. Hydrogen has been detected. Phosphates have been detected. Complex organic compounds have been detected. Hydrothermal activity, meaning hot water circulating through rock beneath the ocean floor, appears strongly supported by the available evidence. Together, these discoveries describe an environment that astrobiologists, scientists who study the possibility of life beyond Earth, consider scientifically compelling. But compelling is not conclusive. As we move through the evidence, a remarkable boundary appears. We can identify molecules. We can estimate temperatures. We can model chemical reactions. We can trace the movement of material from the ocean into space. Yet we cannot currently determine how those molecules are arranged at the level necessary to reveal whether biology is involved. That uncertainty remains central. On Earth, life emerged surprisingly early. Fossil and chemical evidence suggests living systems appeared within the first several 100 million years of our planet's history, perhaps sooner. The exact pathway remains debated, but researchers generally agree that liquid water, chemical energy, and organic compounds played essential roles. Enceladus seems to possess those conditions. Current estimates suggest its ocean may have existed for anywhere between 100 million years and several billion years. Such a range is enormous. Even the lower end represents spans of time difficult for the human mind to grasp. At the upper end, entire chapters of planetary history unfold. But science requires restraint. The honest position held by working researchers is straightforward. No observation has demonstrated that life exists within Enceladus. No observation has demonstrated that life does not exist there. Both conclusions extend beyond the evidence currently available. We remain between possibilities. If future missions discover even the simplest microbial ecosystem, the implications would reach far beyond Saturn. Life would no longer appear confined to a single known origin. The universe would seem less selective, more inclined toward biology whenever suitable environments emerge. Another possibility exists. Suppose Enceladus contains every major ingredient, every source of energy, every favorable condition identified so far, yet remains entirely barren. That result would also transform our understanding. It would suggest that the transition from chemistry to biology may be far more difficult than many researchers currently suspect. For now, the ocean continues beneath the ice, unchanged by our uncertainty, holding its answer whether we know it or not. Long after this moment passes, Saturn will continue along its path around the Sun, following the same celestial course it has traced for billions of years. The planet does not know we are watching. It does not change its behavior for observers. Its vast atmosphere continues to move. Its rings continue to evolve. Its distant moons continue their journeys through darkness. The system endures. Far above the clouds, the great hexagonal storm persists near the North Pole. Beneath layers of ice, hidden oceans remain in motion. Across the rings, countless particles continue colliding, drifting, and slowly falling toward the planet below, Processes that began before human civilization continue today, and they will continue tomorrow. The scale of that continuity can feel difficult to grasp. Human lives unfold across decades, civilizations rise and fall across centuries. Saturn operates on timelines that stretch across millions and billions of years, carrying forward through intervals so large they seem almost detached from ordinary experience. Yet, we became part of its story. For most of recorded history, Saturn appeared as a wandering point of light. Ancient Babylonian astronomers tracked its movement against the background stars. Centuries later, Galileo Galilei observed its unusual shape through an early telescope and struggled to understand what he was seeing. Generation after generation added small pieces to a growing picture. The process was gradual. Improved instruments revealed new details. Better observations corrected old assumptions. Rings came into focus. Moons were discovered. Questions multiplied. But true proximity remained beyond reach until the late 20th century, when engineers and scientists designed a mission capable of remaining beside Saturn for years rather than merely passing through. That mission changed everything. When Cassini launched in 1997, many of the discoveries we have discussed remained entirely unknown. No one had confirmed a global ocean within Enceladus. No one knew the complexity of Titan's chemistry. The strange interactions shaping the rings remained hidden. Entire categories of scientific questions had not yet emerged, but careful observation revealed them. What Cassini ultimately provided was something more valuable than certainty. It delivered questions worthy of pursuit. Each mystery exposed a deeper layer of complexity. Each answer opened additional paths of inquiry. The solar system became richer, stranger, and more dynamic than earlier generations had imagined. There is meaning in that. The rings are gradually disappearing. Unexpected activity continues within distant moons. Atmospheric patterns challenge existing models. The spacecraft responsible for revealing these realities no longer exists as a machine. Its material now resides within Saturn itself, dispersed among the hydrogen and helium it once studied from afar. Yet, the knowledge remains. Saturn completed countless orbits before Earth formed. It will continue circling the Sun long after our world has changed beyond recognition. Against that immense backdrop, a brief interval stands out. Between 2004 and 2017, something built by human hands traveled alongside this giant world, listened with extraordinary patience, and carried its discoveries across space so that you and I could know a little more about our place within the universe.